Hello, my name is Pablo Moriano. I am a research scientist at Oak Ridge National Laboratory in the Computer Science and Mathematics Division. In this video, I'm going to show you how to leverage machine learning and statistical analysis for better protecting the routing cyber infrastructure. This work is done in collaboration with Raquel Hill at Spelman College and Jim Camp at Indiana University. The purposes of this talk for me are to disseminate interest, expertise through a state-of-the-art BGP anomaly detection method, as well as ongoing R&D efforts to network names, background, and data, with the aim of being able to jumpstart discussions and ideas. In that respect, my primarily intended outcomes are then enable synergies through the discovery of linkages, overlaps, and gaps between people in the NSF Cyberinfrastructure community that allows to explore complementary directions, obtaining feedback, either technical or with respect to new research directions, and why not to prepare for future funding opportunities. Among the main key capabilities that NSF has enabled with respect to the cyber infrastructure, I want to highlight three, namely, first, the development of campus cyber infrastructure, second, data-enabled science, and third, scientific innovation. These three key directions are important because they offer the possibility to develop intellectual property, advance the competitive advantage in science and engineering, and advancing campus security. To achieve this, at the intersection, what is really key in these efforts is the health of the core routing infrastructure, which is the main topic of this talk. With that, I will discuss the basis of inter-domain routing along with the current potential threats to the cyber infrastructure. To do so, let's consider the following layer view of the internet. Note that this is different from the OSI model. In particular, each network device assigned with an IP address may be represented at a different abstraction layer. For instance, router redirect traffic to a group of addresses. Internet points of presence house groups of physical routers. At the higher level of abstraction, autonomous systems of ASs represent big networks that make up the internet. The way in which this mapping is done is through group IP addresses. For example, this block. Block of IP addresses can be represented using a compact notation. These blocks of addresses are also known as prefixes. To exchange reachability of information between autonomous systems, ASs, the Border Gateway Protocol, or BGP, is used. In the context of this talk, ASs represent large group networks that have a unifying routing policy, including, for example, universities, internet service providers, corporations, or research laboratories, among others. Here, the real challenge is in interdomain routing, mainly because BGP works based on trust. What that means is, for example, in this hypothetical scenario, is that if AS4, the source, wants to reach address space given by the blue prefix allocated in autonomous system 1, there must be an announcement of the route by AS1. Under normal operation, a prefix announcement is shared among its neighbors. This makes that other ASs learn how to reach that destination, which is stored in the routing tables using the AS path field. Once the information is known and given some other decision criteria, the origin AS know how to reach the destination, establishing a data flow. In this second example, I'm illustrating the prefix propagation process using a different AS level topology. Particularly, the source and destination of the traffic are placed at different locations. Here, the working principle is the same, which means that the routes are eventually learned by the other ASs, which is established in the AS path. Once these routes are learned, there is knowledge of where to transmit the traffic. Now, let me describe different configurations of attacks, also known as BGP hijacks. Unfortunately, there is empirical evidence showing that BGP attacks are escalating in frequency, severity, and sophistication. For example, in 2014, Indosat falsely announced over 300K prefixes. This means that Indosat claimed roughly 2/3 of the internet for almost 3 hours. A more detailed description of this kind of attacks is described in here. In this scenario, AS2 announces the same prefixes that is being announced by the true origin. Given that BGP lacks of authentication mechanisms for origin prefix announcements, these fake announcements start to pollute the routes of other ASs, as is illustrated here in red. The problem with this is that eventually, some of the traffic that was intended to be delivered at the original destination is deviated to a different AS, or the attacker. The consequences of this is denial of service. In the context of the cyber infrastructure, this is not a desirable property because we want always services to be available when needed. A different incident, this time in 2017, occurred when prefixes belonging to financial services such as Visa and MasterCard, and as well as others, were hijacked by Rostelecom. This time, the number of hijacked prefixes was 50, much lower than in the previous incident. During this incident, the traffic of these institutions was briefly routed through Rostelecom before it was sent to its original destination. This incident lasts approximately 7 minutes. This type of incident is also man-in-the-middle attacks because of the nature of how the traffic is redirected. Note that this attack is caused by the same lack of authentication mechanisms for origin prefix announcements. However, the consequences here is that the traffic is redirected. Particularly by announcing the same prefix, the diffusion of this fake route makes other routing tables to be polluted. Now, with these additional routes, traffic from source to destination is subject to pass through the hijacker, as is illustrated in here. Note that after the traffic passes through the hijacker, it is then redirected to the original destination based on the previous established forwarding mechanisms. On this misdirected route, the traffic may be subject to eavesdropping, traffic analysis, or tampering, in detriment, of course, of the confidentiality and integrity of the cyber infrastructure. Current methods for the challenge of detecting BGP hijacks rely on two main approaches. First, cryptographic authentication, and second, anomaly detection. Cryptography protocols include the Resource Public Key Infrastructure, RPKI, for origin authentication, and BGP-SEC, which offers the ability to authenticate the entire path. These approaches are powerful, but they have not been widespread adoption. This lack of adoption is because of lack of incentive alignments and also changes required in hardware. The other approach is then anomaly detection. However, most methods based on anomaly detection are reactive because they identify harm after a disrupted number of updates have polluted some detectable threshold of ASs with fake announcements. The proposed approach aims then to identify incipient incidents before the widely diffusion and harm by identifying an event as they emerge. The main goal is then to identify routing anomalies incidents as soon as possible. To do so, the key observation is on the burstiness of the route announcements. In particular, consider these two event sequences. An event is depicted by a vertical line, X1 and X2. In X1, events are separated at almost regular rates, while in X2, there are bars of events that happen in short interarrival times, and then are followed by periods of no activity. We characterize burstiness numerically by computing the empirical distribution of the interarrival times, here characterized by tau. This notation means that updates sent by a particular AS are then received by a particular collector B, and that random variable characterizes those interarrival times. Particularly from tau, it is possible to quantify the degree of burstiness of the sequence of events by measuring the mean and standard deviation of the interarrival time distribution. For an almost regular sequence, like in this case, the standard deviation tends to 0 and the burstiness then tends to -1. On the other hand, for a bursty sequence of events, the standard deviation tends to be big, leading to burstiness factors similar to 1. Through our experiments, we showed that when there are attacks, the sequence of updates tend to be statistically significantly higher than in normal conditions. That key observation is the basis for anomaly detection measured through the signal Q defined in this equation. To test that hypothesis, we built then an experimental setup using network measurements. Data collection for these purposes relies on broad views, the BGP collection project at the University of Oregon. In particular, route views provide a distributed set of collectors that peer directly with boarded routers and collect their information. The set of collectors are distributed across different parts of the world. We operationalize the collection of BGP updates through an open API called BGP Stream developed by Kata. BGP Stream allows the collection of updates from the collectors for BGP data analysis and post-mortem analysis. In terms of experimental results, in this presentation, I will show you the results for attacks 1, remember Indosat, and attack number 2, Rostelecom, that I previously described. I will start with Indosat. Here, this figure shows the number of updates uniquely originated received by the top 4 collectors. These top 4 collectors were ranked based on the number of routers they peer. Here, the red line represents the occurrence of the incident, as it was demonstrated by different sources. The black solid line represents the rolling mean of those signals. Gray bands represent the number of standard deviations away from the rolling mean. Anomalies are then marked as blue stars. Here, we show that the volume of announcements is correlated with the detected incident. However, as you can see across the number of stars scattered across the time domain, it generates a lot of false positives. We then analyze the effect of burstiness on the characterization of autonomous systems. In particular, the AS marked with the star is the hijacker. Here, in this joint distribution in the x-axis, we measure the burstiness over 1 day of observation. The x-axis shows the number of unique originated prefixes. Here, the red lines correspond to the 95% tiles in each distribution. And as you can see, the hijacker can be clearly pinpointed in the first quadrant. By relying on this finding of a statistically significant burstiness, here we show the time series of the Q signal that is based on the finding of burstiness. Here we use the same visualization conventions as above. By relying on this measure, we show that we are able to detect correctly the beginning of the incidents while considerably reducing the number of false positives by 30% on average. For the Rostelecom incident, based on the volume of announcements, it is possible to find at some extent the beginning of the incidents at the expense of a high number of false positives that are scattered through the time domain. Again, by measuring burstiness here in this joint distribution, remember that the x-axis is burstiness, y-axis is the number of unique originator prefixes, we show that the attacker has a statistically significant characterization in both x-axis and y-axis. Remember that in this figure, red lines corresponds to the 95% percentile of the distributions. Finally, we show that by leveraging the Q signal, it's also possible to effectively detect the beginning of the incident while significantly reducing the number of false positives. In this incident, the proposed approach improved 40% on average the precision in the detection task. In a nutshell, the key capabilities of the proposed approach are the flexibility of continuous passive monitoring of these BGP updates. We also show that during an attack, the AES attacker has a statistically significant burstiness when compared with others and when there is no incident. And that by leveraging this observation of high burstiness, we were able to design and test a detection algorithm with higher recall and better precision than the volume baseline. In terms of future work, the next immediate step is incorporating real-time capabilities to this proof of concept. I also envision to set up a test bed in a cyber infrastructure facility for testing. So please let me know if you are interested. That's all. Thank you very much for your time. Here is my contact information, and I look forward to hear your questions. Thank you.